Hello everyone, I am Shubham, and today I'll be presenting our work called TileClipper, a lightweight selection of regions of interest from videos for traffic surveillance. Before going into the details, let us first understand the current state of traffic surveillance. So this plot from the report from WHO's Global Status Report on Traffic Safety from 2023 shows that there's a consistent number of road accidents happening each year in the last 2 decades. So to circumvent these issues, what cities are doing, they are installing multiple cameras in the order of thousands to circumvent the issue. And this plot from Indian Police Department shows the consistent increase in the number of cameras being installed each year. Now, there's a problem associated with this pipeline. So let us first understand a typical traffic surveillance pipeline, which starts from a camera. Since the camera doesn't have enough compute power, so what they do, they stream the videos to remote cloud servers to run any compute-intensive applications, for instance, object detection, pedestrian counting, and so on. But there's a problem, which is streaming these videos to remote servers incur high bandwidth and latency costs. So how to handle these issues? So what people do, they try to reduce the amount of data that they are sending. And based on the amount of data and the approach that prior works have done, we can categorize these approaches into 3 different categories. The first one is frame pruning, where from the camera captures raw frames and chooses a subset from all the frames which are relevant. By relevant, I mean which shows distinct scenes, but the problem is the camera requires access to raw frames. And for now, no commercial camera generates raw frames. So this is a problem with frame pruning techniques. The second one is quality pruning. So here, the camera first captures frames and converts into low resolution and streams them to the server. The server then upsamples it using super resolution algorithm. But the problem is, since the server needs to run upsampling, so it requires high GPU uses. The third approach is spatial pruning, where the camera selects only those regions from a frame which are relevant, for example, moving vehicles, objects, and so on, and only sends those portions, blackening rest of the parts of a frame. But it incurs high camera side overhead. Now the question is there any way to reduce the amount of data that is being sent to remote server without incurring high overheads at the camera and at the server side? So to address this, we propose TileClipper. I'll now discuss our approach. We propose to leverage tile encoding, which is there in modern video compression standards. But before going into the details, let us first understand what exactly tiles are. So modern compression standards, for example, S265 and so on, gives us a way of splitting a frame into spatial blocks, which we call as tiles. Here, each tile acts as independent video stream, and you can even remove some of them without affecting the rest of the parts. Another good thing about this is you can remove the tiles without re-encoding at the camera. So it reduces your overhead that is being incurred at the camera side. Now, how can we use this idea to save bandwidth consumption? So for this, we did a small study where we sequentially remove tiles from a video, and we observed that removing tiles actually reduces file size linearly. So this implies that if we remove tiles, it can help us reduce the amount of data that is being sent to the server. With the enough background about tiles, let me first introduce the overall idea that TileClipper uses. So we first start with encoding video into tile format, and from there we select the relevant tiles. By relevant tiles, I mean the tiles containing objects of interest, for example, vehicles and pedestrians. And once we select these tiles, we remove the ones that we do not want. And we then send this tile removed videos to server for post-processing. Now, and legitimate question to ask here is, since this entire thing is happening at the camera itself, how can a camera, without you leveraging a DNN, can detect objects inside a tile? So to answer this, we rely on a crucial observation that whenever a tile, so for this plot, we can see this plot on x-axis shows the file size of a single tile, which is proportional to the bitrate. And on y-axis, we show the number of objects that are there in that tile. And we can see there's a high correlation between the file size and the number of objects inside a tile. We propose to utilize this correlation to select tiles. And this is true because the way the video encoding works is if it finds a complex scene, for example, a moving vehicle or a moving object, it requires more number of bits to encode. So can we utilize this correlation for selecting tiles? To understand it intuitively, let us see this heat map. So we have shown two snapshots of a moving car, and the heat map here shows the spatial distribution of bitrates. Here lighter tone means higher bitrate and darker means lower bitrate. And we can clearly see here that wherever this moving car is there, the bitrate of only those tiles are very high. So therefore, this implies that a higher bitrate is a signature of object's presence, and we can utilize them to filter tiles. But this is not going to be very trivial, simply because bitrates in general are very noisy in nature. So this bar plot shows the distribution of bitrate of a single tile across time. So we can see that in general, the larger spikes show object presence, but since the fluctuations are very high, therefore deciding a right threshold is not very easy. Furthermore, the bitrate of tiles also depend on its background and the lighting condition. So for example, on the left side, we can see that even the median distribution, bitrate distribution of different tiles of a single video varies by more than 2 times. And on the right side, we can see that for a single tile, the distribution of bitrate varies with changing lighting condition, and they vary by 30%. Therefore, while deciding the threshold, it's very imperative that the threshold should be adaptive based on the different lighting condition. It should be independent for each tile and should impose and the algorithm that we use for deciding this threshold should impose as less burden on the camera side as possible. Keeping in mind these requirements, we propose a clustering-based tile selection algorithm, which works like this. So we first start with creating 2 different clusters. So these clusters we generate using calibration phase. I will come to it later, but let us first understand how the algorithm works. So we have 2 different clusters. The orange one implies the one that has object, and the blue one contains only those bitrates which do not contain any object. So we first calculate m and nth percentile of these 2 clusters. How do we calculate it? I'll come in a moment. Once we have this m and nth percentile, we take its median and we consider this median as our threshold. So any bitrate value of a single tile, if it goes higher than this threshold, we will mark it as an object tile. And any bitrate that is smaller than this threshold, we will mark it as it won't have any object. And keep in mind that this algorithm works independent for each of these tiles because the distribution are distinct. Now, the question is how to decide on this m and nth percentile. Because if we choose it very high, it's going to give us false negatives, which means we will falsely mark tiles which are relevant as irrelevant. Similarly, if we pick it very low, then it's going to falsely send too many tiles. So we need a right balance between these false positives and false negatives. Therefore, what should be the value of m and n? For this, we use a calibration phase where since at runtime, we do not have access to ground truth, so we cannot calculate the false negatives and false positives. Therefore, initially, what we do in the calibration phase is we first send 60 segments and then exhaustively search for the best m and nth value, maximizing the F2 score. Why do we pick F2 score? Is basically because in traffic surveillance, false misses are way more expensive than false positives, simply because in traffic surveillance, we run safety critical applications. So if we miss out something, it's going to hurt a lot. This was all about the algorithm. Now let me introduce the overall architecture of TileClipper. So it has 2 parts. One is server side and the other one is at the camera side. So let us start with the camera side. So we have camera which generates tiled videos, and these tiled videos we stream first to the server where the calibrator finds the best threshold value that we need to pick. Once it figures out, then it sends it back to the camera, which runs our heuristic, the clustering-based tile selection algorithm, which detects the relevant tiles and filter the ones that we do not need. And these tile removed videos is then again sent to the server for post-processing to run any application. I will now move to the evaluation part. So we utilize 4 different data sets for our large-scale evaluation. First 2 are benchmark data set, and the other 2 data sets that we collected ourselves from India. And so we have a total of 55 videos. We first encode all these videos into configuration of 4x4 tiles and report the object detection accuracy, where we utilize Euler V5 to generate the ground truths. We include 4 different baselines. Number 1 is reducto, which utilizes frame filtering technique. Second is DDS, which uses both spatial and quality pruning techniques. The third one is static tile remover, where we just pick only those areas from the video which are outside row and remove them. The last one is CloudSeg, which uses super resolution for upsampling. And let us now see this trade-offs between accuracy and saving. So we can clearly see from here that CloudSeg is the one that gives the best trade-off between accuracy and saving. TileClipper is similar to DDS, but if we also take into account the server-side GPU use and the savings trade-off, then DDS and TileClipper both are the one that perform worst. And TileClipper is the one that gives the best trade-off between server-side GPU use and savings. Therefore, TileClipper achieves best trade-off between accuracy, server-side GPU use, and the bandwidth saving. We also validated TileClipper's overhead. So let us first see how much overhead does TileClipper put on the camera side. So we can clearly see from this plot that TileClipper is able to achieve more than 60 FPS on the camera. Therefore, it's less compute intensive, while if we see that DDS is not able to achieve real-time performance. On the server side, to process a 25-minute video, TileClipper only utilizes first 30 seconds for calibration, while the other baselines requires intermittent recalibration or continuous server-side GPU use. Therefore, TileClipper puts less overhead on both camera and the server side, making it a more reliable and scalable system. We even deployed TileClipper in real life near our university campus. We can see from the figure here. We installed it in a on a two-way road at a distance of 5 meters away, where the speed limit was 30 kilometers per hour. The road had a mix of pedestrian and vehicles, and we utilized 4G network to stream videos from on-site to our on-hosted server. And we found that the accuracy was more than 88%, while still achieving a savings of more than 50%. To summarize, streaming videos from traffic cameras to remote servers incurs high bandwidth and latency cost. Therefore, to amortize this streaming cost, we propose TileClipper, which utilizes tile filtering to save bandwidth. And we leverage the correlation between number of objects and bitrate to come up with a tile selection algorithm which is light enough to run on both on cheaper cameras. And we evaluated TileClipper on diverse video sets and found that even in real life deployment, it's able to achieve real-time performance and giving significant accuracy and savings. So with that being said, I will like to end my presentation here. So you can, we have even open sourced our data set and code. If you want to tinker around, yeah, you will feel free to do. And with that being said, thank you, and I'll be happy to have your questions.